Did we move something?
No.
It's seeing it. Yes.
Oh, but something wrong. Non-functional. What? Okay.
Yes.
Good. Oh, good. Okay. So I just want to actually, I'd like to start the discussion on the neutrino production, and I need to finish some stuff we couldn't discuss yesterday. So yesterday I introduced some basic of the supernovae. Then just this is general introduction to supernovae. And yes, supernova, we have at least physically the two types of the supernovae, and quark-off supernovae and thermonuclear supernovae. So when you say the type 2, and I will explain what is the type 2 later. But type 2, type 1b, type 1c, so basically they are attributed to the quark-off supernovae. When you have hydrogen, then you have type 2. And you only have the hydrogen removed, stripped, and you have type 1b. And type 1c is that even if the helium is stripped, you have a type 1c. And I ignore the other stuff and the onemag and the CO carbon oxygens. And but in any case, these guys actually the hydrogen lost, and then we call the stripped supernovae. And then, type 1a, it's come from the thermonuclear type. And in this case, people discuss the two possibilities. One is a single degenerate. The white dwarf the degenerate, right? And then supported the density pressure. And the white dwarf and the stir. And in this case, some points, the matter is supplied by the stir. And when at some points, the ignites, and then boom. And then this is then. May cause that type 1 supernova. The other possibilities people discuss is that double degenerate. So there are many detailed discussions about when the white dwarfs merge, and in principle the ignition happens, and the detailed conditions are unknown. But this kind of the setup can also lead to the type 1 supernova. Okay, so what is type 2 and what is type 1a? So basically this is depends on the classification. This comes from the classification based on the spectroscopy. So this is the spectrum, and then when you see the hydrogen, the absorption lines, and then you think this is a type 2. Okay, but some types of supernova do not have a hydrogen signatures. And in this case, they are classified type 1. But among type 1s, actually, some of the type 1 supernova has a silicon signature. These are type 1a. And then if you have a helium signature, and then this is type 1b. And then even if you don't have either helium signature or silicon signature, type 1c. Okay. And okay, we discussed shock breakout emissions yesterday, and what we usually observed, right? Optical astronomers observed, summer emissions, right? Because when it says supernova, I discovered supernova, and then yes, so most of the emissions actually are emitted in the radiation is emitted in what we can see is the visible light, and then. This is roughly speaking, this is a very simplified model, but it's kind of useful to understand what's going on. Because, for example, even if you're interested in non-thermal phenomena, and from this kind of object, because you need to understand the dynamics and this kind of the thermal emissions, because the thermal emission in principle provides seed photons for the inverse Compton emissions, or target photons, or the hadronic interactions. In a sense, actually, if you don't, if you don't know what is going on in the thermal physics, basically you miss some important information. You have some problem in explaining the data. Okay, so this is basically but equation is simple. Basically, this is a time evolution of the internal energies in the confined in the ejector. But the ejector is actually that if you have internal energy in the ejector, basically as the ejector expands, right? Basically, you have the adiabatic expansion. Then in this case, during the adiabatic expansions, so radiation energy is transformed to the kinetic energy. Okay. And this is basically the energy loss. So in the adiabatic expansion, and you also have a loss because of radiation, right? Because ejector, some photons are emitted, and you have heating. And then this heating term actually depends on the physics. And of course, you have some initial input from when the explosion happens. But in principle, when the shock is propagating the star, and in this case, this shock heating is actually the contributes to this heating term. And in addition, usually when the supernova happens, the nuclei synthesize. And then the most typical, the nuclei is nickel. And the nickel decays. And then in this case, you have positrons and gamma rays, and this contributes heating. And then eventually, the cobalts actually start to decay. And then lifetime is actually about 77 days. In this case, they basically, again, this cobalt decays, and the positrons and the gamma rays are produced. And they also give the heating term. Plus, in some situations, the shock propagates there's a dense wind around the star. There's the interactions between the shock and the circumstantial material, which gives the additional heating. And then in addition, you have heating from the central engine itself. It can be jet or wind. But once you give this heating term, basically you can calculate what will happen. Actually, I explained the GW17817, right? In this case, you have the kilonova optical counterparts. Basically, you can describe what happened using this equation. In this case, you can just put instead of the radioactive nuclear decay, but instead of nickel, you need to put the R process synthesized nuclei. And then you can calculate. And okay, what determines the duration? Actually, this is the determinant of diffusion. Then because you guys have discussed diffusion in the cosmic rays, but now actually you need to think about diffusion of photons. Because actually there's an analogy, because I talk about the gamma ray burst, but even in the gamma ray burst, in the initial stage, the system is optically thick. This means that photons cannot get out. Right? The photons scattered with the electrons, and then basically diffuse and inside the ejector. But the diffusion time is much, much longer than the expansion time. Basically, this means that photons cannot get out, trapped. And then when these kind of photons start to escape, basically this gives a kind of the maximum kind of the peak time, determines the peak time. So this is the M is the ejector mass. This is the opacity. It's related to cross section, and with the velocity. The photon diffusion time is given by the tau. This is the optical depth, and this is the kappa is opacity, and rho is the density, and R is the size. So basically you divided the M. This is actually essentially the N sigma R, right? It's a kind of similar stuff, okay? And then in the case of the homologous ejectors, basically the density is M over R cubic. And then this is the diffusion time given by this. And then if you consider that when the supernova happens, so you can approximately assume that the ejector is expanding free expansion. In this case, the velocity is constant, R is Vt. And if you plug in this number, and then you have this equation, and then you can try to solve about T. Then basically the duration is set by the comparison between diffusion time and the expansion time. Then this is this formula. And then basically around this time, basically diffusion time as comparable to the expansion time. Then before this time, the basically diffusion time is longer. Then photons cannot get out. That's the reason flux is lower. And later, the diffusion time is shorter than the expansion time. The photons start to leak, right? Then that's the reason why you start to decline. And in the case of 1987, in this case, the main heating at least around this time is actually the cobalt decay. And after the photons start to get out, basically you see that the declining behavior is consistent with heating come from the cobalt decay, or something like that. Okay, now let's think about the gamma burst. So that we discussed that gamma ray bursts have a connection to supernovae. But in the case of the gamma ray bursts, actually, yes, the gamma ray bursts have associated to supernova. But supernova have you see the absorption line. But gamma ray bursts, actually, first of all, in the case of the famous gamma ray burst, supernova 1998 BW, this is the broad one. This is the type 1c supernova, and you don't see the helium or hydrogen or the silicon. You don't see either of them, and plus you don't see such a big features, line features. So this is because of the velocity is so fast and broad. So somehow the gamma ray burst supernova are expanding quite fast. In the case of these 30,000 kilometers per second or something like that, just in the optical emission region. Actually, the radial emission edge of the ejector is much faster. And then also the GRB supernova are bright, and because if you see the gamma ray burst right curve, yesterday I explained the aftergrowth. That you see the aftergrowth. But around the 10 days, sometimes you see the bumps, which are attributed to supernova. Now, if you look at compare the light curves of the GRB supernova, indeed, GRB supernova such as 1998 BW or 2003 LW are quite bright, and then basically this is a barometric magnitude. Are you familiar with the conversion between the magnitude and the luminosity? If you're an astronomer, probably yes, but physics it's kind of, I give you the formula. But if you just plug in this barometer magnitude, you can actually estimate. For example, in the case of minus 19, basically the order of 10 to the 43 erg per second. Here, the order of 10 to the 42 erg per second. You see that GRB supernova are brighter than the usual supernova. Then we call the hypernovae sometimes. Okay, more energetic. And then this is a kind of the distribution. This is the ejector velocity, and then which is actually measured. Here is measured in radio, and this is the optical. And then in the case of gamma ray burst, you have measurements of the velocity. You can estimate because you know that the Lorentz factor is huge, right, in the gamma ray burst, in the relativistic. And then this is the gamma ray burst often associated type 1c supernova. But you also observe that many type 1c supernova, because the type 1c supernova is order of the 30% of the supernova rate, quark of supernova rate, and then 20 to 30%. And then you can see that a lot of supernova type 1c, type 1bc, and you see that this is the distribution of the kinetic energy. And the usual type 1 BC supernova does not have a fast velocity component, this plot implies. The gamma ray burst, of course, you see the jet and a lot of the relativistic component. Now, you might wonder that apparently there's a kind of intermediate objects, so-called sub-energetic gamma ray burst or low-luminosity GRBs. It's a kind of interesting to ask about the connections between these supernova and the gamma ray burst. And we believe that this connection is actually related to the jet. Because I explained before that GRBs, in order to have GRBs, the jet have to get out from the star. But this condition is not guaranteed. If the jet is stalled inside the star, you don't have GRB, just supernova. But in some cases, of course, you can imagine that in some cases, you can have a kind of intermediate stage, right? Marginally choked or marginally get out. And, in such a conditions, you can have this kind of the object. Yes, so in this sense, people think that low-energy GRBs might be important to understand the connection between the gamma ray burst and the supernova. And then GRB 060218 is one of the famous low-energy GRBs. And because the duration is somehow quite wrong, because I said that typical duration long gamma ray burst 10 to the 100 seconds, but this guy has a duration of 3,000 seconds. And the peak energy is much lower than 5 keV or something like that. And not only gamma rays, and they have a long-lasting X-ray emissions, which looks weird, or also the UV emissions is seen. And then basically the nature is kind of intermediate between the gamma ray burst and supernova. Then we don't understand we don't have a full agreement on the mechanism of the prompt emission again, even in this case. But one of the most popular mechanisms to explain the emission from the low-energy GRBs is the shock breakout emission. So it's actually we explained yesterday, right? In the previous case, we discussed the shock breakout emission from the star. When the shock reaches the edge of the star and the photons start to get out, in this case, the emission is actually expected in the ultraviolet and X-rays. And in this case, actually, is similar, but instead of using the stars, the people consider the wind. Basically, the star, around the stars, there's a wind, apparently. And then you can estimate how the breakout happens. It's a kind of same game. So initially, you can compare the diffusion time photons and dynamical time, and the essentially expansion time. In the beginning, diffusion time is much, much longer than the expansion time. So this means the photons cannot get out. But when the shock propagates in the wind, eventually the diffusion times becomes comparable to the dynamical time. And then in this case, the photons start to get out. This is a breakout emission. And then the theory apparently the kind of it's possible to explain the observed emissions by this kind of shock breakout emissions. And also, this is interesting for the non-thermal emission too. And because once a shock breakout happens, and then basically shock keeps going, and after the shock breakout, actually we expect that the system shock becomes collisionless. When the shock is actually before the shock breakout, basically the shock is actually modified by radiation itself. And we call the radiation-mediated shock. And in this case, typically we don't expect the efficient particle acceleration. Then after the shock breakout, the shock becomes collisionless, and the particles may be accelerated. Indeed, for this guy, it's possible to explain the X-ray data by the inverse Compton emission or by the accelerated electrons. Basically, electrons accelerated, and upscatter the thermal emissions, and then X-rays are produced. And then how you can have this kind of fast jet, because in the case of the low-energy GRBs, we have a very fast velocity component. Actually, the Lorentz factor, the velocity is 0.6 c or 0.8 c or something like that. So they're quite fast, right? Almost mildly relativistic. Lorentz factor is order of 2 sometimes. Then it's not so easy to produce this kind of the mildly relativistic ejector. Then one of the popular possibilities is actually the jet-induced explosion. Because when the jet is choked, because jet is relativistic, right? The jet is choked, but eventually you have, jet pushes the material, and this material can still remain more or less mildly relativistic, but not ultra relativistic, right? Because a lot of material is there. Yes. And then the plus, after the shock breakout, you expect non-thermal emissions. And then this kind of, because the particles can maybe accelerate it. And then, so I skip this. And then this is the low-energy GRBs. And then also the important in view of the energetics, because they are dimmer in gamma rays, but more frequent. So if you calculate the luminosity density, basically the usual gamma ray burst or late density of the gamma ray burst, 1 per gigaparsec per 1 per gigapascal cubic per year. But instead, oh, sorry, this is not erg per second, this is erg, sorry. So the total gamma ray energy tends to 50, isotropic total equivalent total gamma ray energy tends to 53 erg or something like that. Low-energy gamma ray bursts actually the much dimmer, but more frequent. And then this means that if you are interested in the ultra-high cosmic rays or accelerated cosmic rays, the people think that this population might be important as a sources of cosmic rays, because ejector is mildly relativistic or subrelativistic, and it's all of the fraction of the speed of light, and it's more abundant, and it can be a good accelerator of the cosmic rays. And then also the might be more baryon rich. That's the reason why it's kind of the the nature is different from gamma ray burst. Okay, so I just also want to explain that. Sorry, from 2:34, right? I just don't know the exact time. So
I will give you 10 minutes. It's let's say that you have 1 more hour.
Okay, 1 more hour. Okay. Okay, so there's a luminous supernova. This is a recent observations. Actually, started to find many different types of the Kolakov transient. So I explained the gamma ray burst, and I said that they mentioned the long CGRBs, but optical astronomers start to find that not only usual supernova, but also the very bright supernova. Start to find the very bright supernova, so-called the superluminous supernova. So basically, the superluminous guys exceeds the absolute magnitude is order of the 10 to the minus 21. No, just minus 21, sorry. Just minus 21, which corresponds to the order of the 10 to the 44 erg per second in luminosity. And then there are apparently there are this couple of classes of superluminous supernova. The superluminous type 1 is basically, again, the hydrogen poor. And type 2 is the hydrogen there. And we believe that at least some of the type 2 superluminous supernova are powered by interaction with circumstellar material, which is actually interesting in the view of the stellar evolution theory plus particle acceleration. This is one of the examples. The type 2 N supernova, the N is actually the reason why you say N is that astronomers see the hydrogen line. And this implies that at least in the outside of the ejector, there's a lot of material, and the cold material exists. Then because cold, then you see the narrow line hydrogen. And then this type 2 2010 gel is actually you cannot explain by the radioactivity, and then the interaction is happening. Then in order to explain this, the phenomena, people think that it requires mass of the circumstellar order of 10 solar mass. And in the case of the type 2014 C, is actually we see the brightening. Initially, it's observed the type 1b, but later actually they start to see the hydrogen signature, and it's a chameleon supernovae because they change the type. And then later you start to see the brightening the X-rays and radio, and this is the evidence that a lot of material exists, and then there's apparently the 1 solar mass of the circumstellar material exists. And this is apparently happens in many cases. So for example, this is a famous type 2N supernova 2009 IP. This is a supernova, believed to be supernova, but just before the 40 days, they have a kind of a very bright bump. So the people interpret this phenomena as a mass ejection. So before the supernova explodes, something happens, then mass is ejected, a lot of mass ejected, then a true supernova happens. And apparently this kind of the phenomena is probably happening for some types of the stars, massive stars, such as luminous blue variables. And if you look at some observed luminous blue variables, sometimes some of the objects are observed supernova imposters. Because mass ejection happens so bright, and then you can misunderstand this transient as some relatively deep supernova or something like that. And but it's not supernova because this can repeat a couple of times. And then probably the famous example, the Eta Carina. Eta Carina is actually the very massive star which exists in our galaxy, this guy. And then this guy, actually sometimes people, astronomers observe that big mass eruptions. And the huge solar mass of the materials ejected. And then, then we don't, and for such a massive stars, actually, there are, for example, one of the promising mechanism mass ejection pulsation pair instability, but I don't have time to explain this detail. Okay, so one more thing, type 1 superluminous supernova, these are hydrogen pure. So this is probably people think that it's difficult to explain. Well, depends, but many people think that this can be more nicely explained by the energy injection by central ranging. So one of the popular possibilities is a pulsar scenario or magnetar scenario. Basically, this guy, the supernova type 1, is actually, again, the very broad feature, and it's very difficult to explain by the radioactive nuclei and heating. And then instead, the people put the magnetar, then basically the spin down power. The rotation energy is somehow converted to the thermal energy. And then if you admit these assumptions, you can explain the light curves by these kinds of the pulsars. And then it's for example, this is kind of interesting because, for example, one of the gamma ray bursts actually is it's the associated supernova. And this supernova is similar to the kind of light curve of the superluminous supernova, or the luminosity is a bit dim. And then this kind of GRB supernova can be explained by the magnetar activities. So some people actually, so this supernova has a so-called also the kind of weird characteristic. So somehow duration is very long. And then people call the ultra-long GRBs again. Because you said that the typical duration of the gamma ray burst actually is 10 to 100 seconds for the long GRBs. But some of the long gamma ray bursts have a duration of 10 to 4 seconds, hour. So yeah, so maybe the people actually speculate that this kind of superluminous supernova and the ultra-long gamma ray bursts are actually related. And then this is a paper from Brian Metzger. And he actually tried to explain the diversity of the superluminous supernova and the gamma ray burst and by the activities of the neutron stars. So that if the neutron star is the very first and strongly magnetized, you have a gamma ray burst. In the intermediate, in between the ultra-long burst. If the magnetic fields are relatively weak, in the sense still strong, 10 to 13 to 14, and then you can actually explain the superluminous supernova. And then in principle, you can try to explain the supernova type 1c. Basically, yes, by putting the magnetars, the pulsars, basically you can try to make a connections among the different types of the quark corpus objects, and from the gamma ray bursts, ultra-long GRBs, superluminous supernovae, and this is the kind of the questions we have now. Basically, which kind of the engines that drives this kind of supernova. So this is a kind of summary diagram. So yes, so we start to find the different interesting types of supernovae, but people think that these are kind of related engine activities. Can be winds powered by the pulsars, or possibly the black hole plus accretion disk, or maybe the jet may itself, jet may control, and then jet is actually choked, and in this case, this kind of activity can also can be also regarded as engine. So okay, so I finished this connection between the GRB supernova. So basically, diversity supernovas exist, and the gamma ray supernova actually the hypernovae or transrelative supernova, and then maybe the jet winds may control that kind of diversities. And now that we have a superluminous supernova, And I don't have time to discuss another transient, which is interesting, fast Brute optical transient. And different types of the transients have been found. And then we don't understand what makes this kind of diversity. And this is actually one of the important questions for this kind of transient astronomy. And in this sense, to address these questions, neutrinos gravitational waves are important. People expect that it will be kind of great. Also, the high energy signatures can be useful to probe this kind of the transients. Indeed, for some of them, actually, the X-rays, the gamma rays, X-ray data and the radio data are quite important. Okay, good. Then let's move on. Do you have any questions for now? No. Any question? No. Okay, so yes, I'd like to move on the neutrino productions. Yes. So I think I already gave a talk in the colloquium, and basically the high energy neutrino astrophysics has started, and then probably there are many questions. And one of the central questions, of course, the origin of the high energy cosmic neutrinos, and what is the production mechanism, the proton-proton interactions, or proton-gamma interactions. And then maybe you might wonder what is the connection to ultra-high cosmic rays. And then what is the connection to gamma rays, basically multidimensional connection. And then characteristic contributions, and what is the neutrino transient, the flavor ratio, new physics. This is actually a question related to particle physics. And then okay, if you want to understand the cosmic neutrino origins or mechanism, you need to, if you're a theorist, you have to work on the three things. I think first of all, actually, dynamics is important. That's the reason why I spent a lot of time in the source physics, because basically this depends on the energetics, right? So that you need to know energetics. Energetics is basically the related dynamics. So how the outer flows evolves, then what the energy source, what is the velocity of the outer flows, what is the characteristic, the composition of the outer flows, how many baryons entrained, pair there, then how much is the magnetic field, and then what is the dissipation process, and shocks or reconnections. Of course, the problem is that in the case of the jets, you have many unresolved problems, but still important. You need to keep in mind that this kind of dynamics actually are very important, even if for the modeling the neutrinos. For example, I basically in the previous sections actually I explained the thermal emission, the supernova, but thermal emission is actually related to dynamics. And the thermal emission actually provides the seed photons for the neutrinos, the neutrino production. And then if you ignore, then basically your calculation can be inconsistent with what we observe. The good thing is that some cases, we have a lot of data which are available. So this kind of information is kind of quite important to understand for the calculations. And then yes. So probably the best example is actually the supernova remnants and the gamma ray burst aftergrowth, because to describe the dynamics, and you can approximately use self-similar solutions, right? In the case of the supernova remnants, you can use the self-Taylor solutions. Then I introduced a Brown-Ford-Mackey solutions yesterday, right? In the case of GRB aftergrowth, you can use it, right? This is a simple model, but you can use it. And then in principle, you can do the simulations. This is the most sophisticated approach. Basically, you can run the code of the hydrodynamics, MHD codes, and you can implement the radiation in your code if you want. And in this case, you do this kind of calculations, and then you can actually do the calculation. In principle, you can perform the more sophisticated calculations. But so far, in many cases, for the purpose of the comparing the data, because still we have a lot of uncertainties, many modeling that relies on the single zone model. And in the sense that people just consider that the characteristics emission region, they calculate neutrino production there. And then again, this second step is probably particle accelerations, and this happens in plasma scale. And then shock, people consider shock accelerations and the reconnections and the electric fields. And then yes, so if you know if you are sure about the acceleration mechanism, you should implement the particle acceleration process in detail. And this is doable for the supernova remnants, or some cases, right? Because you can do that. But in the case of jets, and because unfortunately we don't know the exact mechanism, then basically what people do is that, as I said, that people just put the power off for simplicity. But if you have a good theory, you can implement the details. And then once you have two ingredients, and then this part is actually quite automatic, as long as you know this is a microphysics part. So particle physics are known. So for the standard model, then you can take into account these elementary processes. So if your electrons are accelerated, you need to take it in leptonic processes. For neutrino productions, hadronic process is important. And then, as I said, important to think about heating and thermal processes. Some people forget, but it's sometimes quite important. And fortunately, because of the progress in the observational astronomy, astrophysical electromagnetic data are often available. So I think that this part is Pascal already explained. Just I flash the different processes. And the leptonic processes, you have a synchrotron process, and then basically the electrons, they emit radiations because of magnetic fields. And then inverse Kohta emissions, in this case, high energy electrons upscatter the photons, and then you have high energy gamma rays. And the hadronic processes, actually, people typically consider two processes. One is proton-proton interactions, hadronuclear processes. In this case, the protons hit the other nucleon and making pions. And the other process is hadronic processes. In this case, proton interacts with low energy photons, and again, the pions produced, and these pions decay, and then you have neutrinos, gamma rays, electrons, and positrons. Then this is a kind of typical cross section of the PP cross section, and it's a kind of what is the scale. And then this is natural unit, by the way. And this is the energy of protons in the rest of frame of the target proton. The cross section is typically dimensional cross section is actually the length square, right? And if you use natural unit, it's basically the 1 over m, right? And the 1 over m because c and h bar is unity. And then in this case, basically you cover interactions, right? It exchanges the pions, right? And then basically, roughly speaking, this it's not exact actually, but crudely, you can put if you plug in the pion, component length of the pions, and then in the square, this is a 30 millibarn, which is comparable to the PP cross section. And then typically, when protons hit the proton, other protons. 50% of the proton is actually the parent proton lose 50% of the energy. Basically, this is a kind of related energy transfer fraction. And then 20% of the incident proton energy is actually used for the pion production. But if then how the pions, how many pions produced, how the distribution pion is, depends on the energy. And in the case of PP interactions, so that if you inject the very, very energetic protons, a lot of pions produced, many pions produced. But most of the pions actually they're very low energies. And then if you this is a kind of number distribution, and you see that the number is actually a lot of low energy pions produced. Especially if you go to high energies. This is the injection energy of the 100 GeV protons. If you put the PV protons, you see that more low energy pions produced, right? This is a pion distribution, number distribution. And then, but for the calculation of neutrinos, the important quantity is actually the peak of the energy distribution. Basically, what is the peak in the energy spectrum. And then you actually, this is a number distribution. In order to convert this to the energy distribution, you have to multiply x, okay? If you multiply x. And actually, if you multiply x, actually, it's harder. And this is the peak. So basically, what I said is that in the case, this is something like this. But if you multiply the x, fx, right? If you multiply the x, 1x, and in this case, you have something like this. And this is here. So basically, typically, on the pions, if you read that this peak of the energy distributions, this is a 10% and 20% of the parent proton energy. So this actually gives, if you want to estimate the neutrino energy by PP interactions, this is a useful number. So P gamma interactions. In this case, this is a cross section of P gamma interactions, and this is the energy of the photons in the rest of frame protons. In the case of P gamma interactions, actually you see a lot of resonances. Actually, even in the PP case, you see the resonance here, but it's more difficult to see. But in the case of P gamma interactions, yes, so that you have the delta resonance, which happens in where the energy of the photons is around 0.3 GeV, and you have another resonance. And the high energy, if you go to high energy, the cross section gradually increases. So the important thing is that in the astrophysical case, there's a difference between the PP and the P gamma, because in the case of PP, usually protons, you have a cosmic rays, and the cosmic rays are mostly, important thing interaction. The cosmic ray interacts with the cold gas, lot of gas, and then you can see the calculated neutrinos. Because the cosmic interactions between the cosmic rays themselves, of course, the cosmic rays number density is lower. Then yes, cold protons are more, right? Usually, right? It's just thermal protons, low temperature protons, actually more. You have more target. Typically, this kind of interaction is more important. But the P gamma interaction case, actually, the photons are actually massless. That you have a kind of broad distribution. And then, if you consider very high energy protons or low energy protons mainly interact with the high energy photons via this kind of digital resonance. The higher energy protons interact with low energy photons. So basically, you can try to find the photons which resonate with proton for the given energy. And then cross section is actually a bit lower because you have a kind of alpha and the fine structure constant. And then this is all of the milliband, and the milliband is 10 to the minus 27 centi square, okay, 27 centi square, and then it's all of the 5 times 10 to the minus 28 centi square. And then, okay, the threshold energy. I think this can be a good exercise, right? Threshold for this kind of the business, actually, because you hear the considering problem that this is a proton rest frame. The proton is rest. Okay? And then the question is that this photon, what is the minimum energy of photon which can produce pion? Then this is a kinematics problem in the special relativity. Okay? So I think it's very similar to what the Pascal discussed. And then, of course, if you address this kind of questions, you can imagine what happens in the center momentum frame. Momentum frame. In center momentum frame, okay, it's a bit better with photon. And then in this case, photon is here, and the proton is here. This is the initial state. Then when they collide, what is the minimum condition to have pion? So this is exactly just one proton and the pion, right? Right? Just a proton plus, because the proton is coming, right? Then just pion is produced, the center momentum frame, right? Right? And in this case, basically the in natural unit, the MP plus M pi, right? So the total, total energy is MP M pi. And this square is actually the Lorentz invariance quantity, so-called S. Okay, this is Lorentz invariant quantity. But you can also calculate this Lorentz invariant quantity. And basically, you can calculate this quantity in this frame, too, right? Something like that, right? Because a proton doesn't have momentum at 0, and then the photon is massless, and then you can do this calculation, right? And then if you do these calculations, and then you see that and then this cancels out. Right? And then this is cancelled out. And then you get that E gamma threshold. And then M pi. Sorry. It's better to say M pi. Something like that, right? Is okay? The same thing. So this what I get, this threshold energy. And then practically, do you know the pion mass? Sorry? Roughly. Yeah. Do you know pion mass? Actually, I essentially give the answer. 140 MeV, roughly. Okay, so the charge point is 135, and neutron point is 135 MeV. So roughly speaking, 140 MeV, right? Neutron pion. Okay, so the 140 MeV is the test pion mass, and the proton mass is basically the 0.94 GeV, right? And the proton mass is much heavier. And essentially, you can ignore this term. So basically, this implies that when the photons actually photon energies are actually near the pion rest mass energy, that you can start to produce pions. Now, physically makes sense, right? Okay. And then basically, resonance happens in the bit higher energies because this resonance happens when the delta particle is produced. So delta particle is actually the kind of the mass is 1.2. Okay, there are different delta particles. The one of the most famous delta particle is the delta plus. This is the order of the 1.232 GeV, and then basically you can similarly calculate this, right? If you want to calculate this delta resonance energies, E delta, what you need to do is that you just replace here, right? You just replace here is just I put M delta, okay? Just you replace, and then basically you can repeat this kind of calculation, right? And then I think that you don't have to write down. Maybe you can see, right? Because this is the m square, then the e square can cancel it out. Then you can see that the m delta square minus mp square, then divided by the 2mp. Then you can see that from this part, from this part, from this part, from this part, you can see that you can get this equation. Okay? And then if you calculate this number, if you plug into this 1.232 GeV, the resonance energy is 0.3 GeV, kind of the 340 MeV. And then one question is that, okay, this is again the frame problem. So in the gamma ray burst case, I already discussed 2 frames and 3 time scales, right? Then you need to exchange the kind of perform the Lorentz transformation. If you want to work on this kind of problem, then you also need to think about the transformation in the particle things, right? So in this case, I discussed usually cross section is actually given as a function of the proton rest frame, okay? Proton rest frame. But here I consider center momentum frame. But what you want to calculate is actually in the comoving frame of jet, right? Because this is what you want to calculate. Typically, you think that distribution of the photons is more or less isotropic in the comoving frame of jet, and then cosmic rays are also regarded as isotropic distribution in the comoving frame of jet. This is a kind of zeroth order approximations, and people usually take. And then in this case, you need to again think about the relationship. Now, I have to skip, but you can actually the same thing. You can calculate this factor, okay? This factor, right? This S. And in the plasma comoving frame for the given energy of the proton energy in the gamma. And then usually it depends on the, the angle between the 2 particles. But you can calculate this kind of the relationship for the given angle, okay? And then roughly speaking, if you average out this angle, the basic relationship between the proton energy and the gamma ray energy is the order of 0.GeV square. This gives a resonance condition for the protons and photons in the P gamma interactions. Okay. Then after you make a pions, right? Because then even in the P gamma case, basically the pions carry about 20% of the parent proton energy. Okay, in this, typically in this plasma frame, basically the proton's energy is much, much higher. The photons are lower. Basically, the pions produced, but this pions actually takes the energy from the parent proton. And this is typically about 20% of the parent proton energy. And then you can actually, you have pions. Then if you want to calculate the neutrinos, gamma rays, and of course, in the reality, you need to calculate the decay. In the case of the neutron pions and the charged pions, you have 2-body decay, right? And this is kinematics. And the pions, spinless, the spin 0, right? And you can calculate this 2-body decay spectrum. But again, this is I have to skip the detailed derivation, but this is not so difficult. So the muons decays into the muon neutrinos, electron neutrinos, and electron positrons. This is again this case a 3-body decay, and here weak interactions. And then this case is actually a bit more tricky because the muon has spin, and neutrinos are only left-handed. You need to think about this. And then, but still, it's possible to calculate this kind of decay spectrum. But I don't, make a derivation for this decay spectrum. But important thing is that these charged pions, muons are decaying the weak interactions, and the pions, the neutral pions decay in the arithmetic interactions. And then in the case of neutrinos, typically the neutrinos and the positrons, the electrons carry a quota of the pion energy, roughly speaking. And then in the case of the, the gamma rays, okay, of course, this is kind of obvious that typically, because the photons share the energy of pion, basically the half of the pion energy is carried by one photon. Okay. So this implies that, okay, if you combine this fact, right, in the case of the p gamma interactions, you say that I said that pion basically carry the 20% of the proton energy. Okay, this is what I said, right, in the before. And the neutrinos carry the quota of the pion energies. And then this implies that typically neutrinos carries the 1/20 of the parent proton energy. So this is kind of useful to imagine what happened. For example, the ICTP detected 1 PeV neutrino, right? Or even higher. So that let's take the highest energy one, the 9 PeV neutrino, right? 9 PeV is about 10 PeV, right? Then 10 PeV neutrino, if you discover the 10 PeV neutrino, at least the protons or energy per nucleon has to be larger than, it has to be around 200 PeV. So the cosmic rays have to be accelerated around 200 PeV or something like that. Typically. Of course, it's dangerous to make a discussion on only one event, but typically. And there's one more piece of the information. So the basically is that, okay, once if you know the interactions, basically if you know the particle physics, for a given spectrum of cosmic rays, for a given spectrum of the gamma rays, or gas density, you can calculate neutrinos spectrum and the gamma rays. You can do that. But reality is what I need to, basically what IceCube sees. Actually, I already said the diffuse flux. Diffuse flux is actually the kind of the contribution, this is the sum of the contribution from all the sources which exist in the line of sight, right? For given directions, because you have many sources, right? And from the redshift local sources, redshift 1, redshift maybe perhaps redshift 5 or something like that. You need to integrate the contribution from all over sources. Then basically, this is also the kind of depends on the cosmology, but you can do that. And this is the mean diffuse intensity. So basically, this is the formula, and this is the integral over the basically the time, and basically the integral over the cosmological distance. And then this is a neutrino spectrum per source, and neutrino spectrum and per volume. And then this is a redshift evolution. And then this actually depends on the sources. In the sense, if you think about the galaxies, the supernova, this traces a kind of star formation rate, which has a peak around redshift 1 or 2. But if you think about different sources, it's different. But then, but you need to do that. Even you can calculate if you know the physics, if you know the astrophysics, source physics, and particle physics, particle acceleration, everything, you can calculate this, okay? And then also you need to know the source density. And then if you know the evolution of the sources and how the redshift is evolved, you know this factor, and you can estimate the diffuse flux. Okay, one example, which is a kind of famous example, and then this is a cosmogenic neutrinos, so-called GZK neutrinos. And then I think that Pascal has already discussed, explains, the GZK process. And then ultra-high cosmic rays, interact with CMB and EBR, accelerated background, right, by P gamma interactions, right? And in this case, neutrinos gamma is produced. And then during the propagations, you have a kind of the neutrinos coming from this GZK process. This is cosmogenic neutrinos. And the first suggested by Berezhinsky is that spin. And then you can actually estimate the peak, roughly speaking. Because I already explained that, in this case, the target energy of the CMB is epsilon CMB, right? Then typical energy of the CMB is, do you know the number? Okay, what's the temperature of the CMB? Yes, okay. Then you can just convert to the electron volt. Then basically you have a KT, right? The KT, then you just divide it by the, then you can convert from the erg to the electron volt. Okay, so it's order of the 10 to the minus 3 electron volts, 7 times 10 to the minus 4 electron volts, or something like that. And then if you plug in the 10 to the minus 3 electron volts, or something like that, actually you get that the corresponding energy, the resonance energy is actually, the proton energy is around 10 to the 20 electron volt. Then 10 to the 20 electron volts, then, as I said, right, this is the 5% of the parent proton energy carried by the neutrinos. And then in the simplest setup, and then if the energy is extended, the proton spectrum is extended to high energy, that you expect that the neutrino has a peak around 5 times 10 to the 18 electron volts. This is a crude estimate. And then it's a reality is actually that there's a redshift effect. Actually, that you see that a bit lower. And then also, I think in this case, there's some subtlety, but it's order of the 10 to the 18 electron volt. And then indeed, actually, you can estimate what is the typical energy of the neutrinos, and based on this kind of the consideration. Okay, and then I don't explain this kind of stuff, but if you know the kinematics of decay and then of these spectrum, basically you also understand this kind of behavior. Basically, here the low energy stuff is actually simply determined by the kinematics of the Pion decay. So the spectrum is actually proportional to the two. Okay, now let's discuss the source stuff. And then I think that using the rest of my time, basically I want to give the examples of how we can estimate the neutrino production in the gamma ray burst, because we discussed gamma ray burst. So as I said, that depending on astrophysical situations, you can think about the both of the. You need to think about both of the p gamma interaction, the pp interactions. But typically speaking, in the case of the galaxy clusters, usually the pp interaction is more important, and the interaction with gas is more important, and except for the high energies. Very high energies. And then in the case of the p gamma in the case of the AGN gamma ray burst, it's more p gamma is more important. This is you can imagine, right? Because the gamma ray burst blazers AGN super bright, and you have a lot of photons in there. And then it's more if you compare the target density, number density of photons, and the number density of the gas. In this case, the number density of photons is actually more. And then spectrum is actually tends to be different. And then this is actually, again, related to particle physics. If you consider power of spectrum, and then in the case of PV interactions, and because gas, if you target the gas is cold, basically neutron spectrum is also power law. If you put a power law, spectrum of the neutrino is also power law. But in the case of p gamma interaction, the story is different. The reason why is that this is different is that the resonance is important in many cases. Actually, if the non-resonant interaction is important, actually you expect a similar behavior, actually. But if the non-resonant interaction is important, what happens is that, okay, the low energy photons mainly interact with the high energy photons. Low energy protons mainly interact with the high energy photons. Higher energy photons, high energy protons are mainly interact with lower energy photons. The astrophysical setups in the gamma ray burst and AGN, and then not always, but in many cases, if you calculate, if you look at this kind of, actually I explained this plot, right? Nu F nu when I described afterglow, right? Afterglow theory yesterday, right? And then, for example, I put the nu M, and I put the nu C, and then this is something like this, right? This is a minus 2p, and this is a kind of the minus 2 p minus 1, right? Right? And of course, the story is different if you go here, but as long as your protons interact with photons around these energies, basically this spectrum implies that the number of photons is more at lower energies. Okay? Right? This is number density, related number density. This is basically the photons, basically the, I don't know, the percent square per, the related to percent square the per second, right? It's more exactly the something. Yeah. So in this sense, in the many cases, you can find more photons at low energies. And then if you put the power laws, basically you can find more photons and at higher energy protons. The efficiency increases, right? You have more targets. Basically, even if you put a power law, the cosmic ray spectrum, the neutrino spectrum can be harder than what you inject when this kind of setup is justified. Okay. Okay, let's talk about the gamma ray burst. In this case, cosmic rays accelerated, and the electrons are also accelerated. And then this kind of people think that let's take this, synchrotron model. In this case, photons are produced by the electrons. Then, in particular, we discuss different phases, but let's focus on the internal shock case for simplicity. So yes, so basically, what you need to have is okay. So first thing is that this is a kind of simplest setup. First, to calculate neutrino spectrum, you need to know the cosmic ray spectrum. Okay. Then, if you calculate the more sophisticated way, that you can do that. But just for simplicity, let's take the simplest Fermi spectrum, and which will be discussed more tomorrow by the Pasquale. But let's take the very flat spectrum, e to the -2. The energy spectrum is very flat, and then something like that. And the photon spectrum, yes. So I said that typically described by the band function, the broken power. Then this kind of business, I just assume the broken power, then rising with 1 and flat. And then you can calculate the efficiency of the Pion productions using these conditions and the optical depth. Okay, so the first thing I should think that, okay, what first question I would ask you is that observed energy of gamma rays in the prompt emission is 1 MeV in the observed frame, okay? What is the typical energy of the neutrinos? Or this is a goal. What is the typical energy of neutrinos coming from the protons which are interacting with the MeV photon? So the first thing, what is the resonant energy of the corresponding? So you can actually use this kind of relationship, but there's one difference. The Y is that because the jet, okay, this is the particles where the accelerated and the photons are emitted, but this region is moving with the Lorentz factor of the gamma. So I actually said that this condition, right? This is this. But this is actually the given in the plasma frame, the kind of the frame of the co-moving frame of jet. And in a sense, okay, if I denote if I use a notation that co-moving frame is a prime, actually you need to put the prime here, okay? And then what is the relationship between let's ignore the redshift, and then what is the relationship between the observer frame and observed energy and the co-moving frame energy? Yes, just gamma. So the EP is a kind of gamma, EP prime, and E gamma is a gamma, E gamma is a prime. And if you plug in this, and then you have gamma square. You need gamma square. Actually, in one of the exercise problems, actually I discussed gamma-gamma interaction. Actually, same exercise. In the gamma-gamma case, actually, just instead of putting the protons, you can consider gamma. And of course, the kinematic condition is different. But the calculation is in this level. Of course, the physics is different, and the microphysics is different. The calculation in this level is kind of has an analogy. Then you have this, and then you can plug in this is the observed energy, right? And then you can plug in the 1 MeV. And this is 10 to the minus 3 GeV, right? And then you need to know Lorentz factor. I think in this case, I put probably the gamma is at 300, I guess, typical number. So if you put this gamma Lorentz factor is 300, or something like that, then basically the gamma square is 10 to the 5, right? In this case, just the order of estimate, 10 to the 5. Then if I put 10 to the 5, 10 to the minus 3, and then you get 10 to the 8, 2 times 10 to the 8 GeV, right? And 2 times 10 to the 8 GeV is at 2 times 10 to the 17 electron volt. This is 20 PeV. Does it make sense? Okay. And then basically this gives what is this kind of estimates the horizontal direction, right? For the given energies, what is the most important proton energy which interact with this kind of photons. So next important quantity is the kind of how much normalization, right? How much is the efficient? For the probability of the Pion production, right? When the protons, they interact with photons, the how efficient is the interaction. Okay, this is the related optical depths. Basically, this is the probability. Again, the same thing. Okay, reality is actually that you need to use the exact formula, and probably I think the Pascual will discuss this exact rate, right? So basically, it's a relative velocities you can write down, but for today, because I don't have much time, basically I try to do the simplest estimate based on the optical depth. Basically, for the given energies, and then basically you can calculate that basically optical depth is this is a kind of the probability, related probability. It's a and then in this case you can calculate the unit the number of density of photons, right? And the cross section and the size. Okay? And then this is again we are working common moving frame. And then as I explained yesterday, this is R over gamma. And this part is actually it's related to one of the problems in the exercise. And then basically you need to do the calculations. And if you calculate, so if you have the spectrum in the observer frame, is something like this, L. Let's say this is the L peak, and this is the E peak. For example, how you can calculate the peak number density of the photons at peak energy, at peak. So basically the first thing, you need to L peak, right? But you need to think about the conmoving frame. What is the conmoving luminosity? Actually, this is also related to the question of the redshift stuff. Actually, the luminosity distance and why, when you calculate why, when you calculate the flux, you use the luminosity distance, right? And then you have the 1 plus d square, and when you calculate the flux. The reason why is that basically in the conmoving frame, basically you need actually the conmoving luminosity is actually the gamma square. because the energy is one erg per second, right? One is a erg, energy is boosted, and the other is a time dilation stuff, and gamma, another gamma. You have a double gamma, okay? And then basically you have the 4 pi r squared c. This is the usual stuff. And then this is the energy density in the comoving frame. And plus you need to put the peak energy. But again, in this case, the comoving energy, because I already converted the comoving frame. Okay, does it make sense? And then if you do this, basically you have a peak 4 pi RC gamma E peak. And then because if I change the comoving frame to observer frame, you have something like this. So as a result, basically if you plug in this number, so you have the R square and E peak and gamma, okay? And then you have another gamma here because of comoving size. And then you have a gamma square inverse, right? This is a gamma to the -2, right? Is it okay? Then this R2, this R square, this R square, R, just R. Then you have R to the inverse, okay? You have this dependence. The cross section, the probability of the P gamma interaction is actually the proportion to the R to -1 and the gamma to the -2, okay? And if you use this relationship, you run this, right? R is a proportion to gamma to the 2, gamma square T, right? If I plug in this number, and then basically this is the variability time scale, the delta T minus E1, and gamma to the -4. Then you can imagine that this kind of calculation is very sensitive to what you assume for the Lorentz factor, the basically sensitive dynamics. Okay. And just for completeness, so that here I estimate the probability. Then why I put this plug in the number, because this is actually I related inelasticity. Because, for the definition of these factors, more, strictly speaking, what I need to calculate is that energy loss length and the ratio between the dynamical time over the ratio of the dynamical time to the energy loss length here, okay? So basically this factor. So this is the energy loss time. Basically, this is the energy loss time scale. Energy loss time. Energy loss rate due to P gamma. So for the practical, for the detailed calculations, basically you need to calculate this energy loss time scale rate using the detailed cross sections and spectrum. I think that this kind of formula, I think Pascal will discuss probably tomorrow or the day after tomorrow. Okay, but you already get the sense, right? Just you estimate this kind of the target number, estimate the number density of the target photons cross-section size, you can actually estimate what would happen. And then basically using this, if you calculate this number, so what you get is that spectrum is actually this is a Pion spectrum. Then you have this dependence. The reason why is that if you go back to this is the energy spectrum, okay? This is the energy spectrum. So that if you convert the number spectrum, right? Then this is flat and -1. Okay? Okay, well, it's probably, I will finish. So flat, okay? basically, as it says, the very high energy protons. This is the proton spectrum, proton's energy. This is a kind of the EPB. This is a kind of proton energy of protons, which has a resonance of this photon energy. Okay. Higher energy photons, for example, here, these protons interact with this region. Okay. So this energy, this E1, this E2, the energy proton with this epsilon 2 has this energy. Photon interact with these photons. Okay. Okay, does that make sense? Resonance. So apparently you find that lower energy photons find less target photons. Higher energy protons, basically the number of photons is saturated because the spectrum is flat. Okay? That's the reason why if you assume the power of this kind of flat energy spectrum, because the number density of target photons is saturated for high energy protons, because the number density of low energy photons is saturated, then you see the flat spectrum in the Pion spectrum. And then for the low energy pairs, because the number density of the photons is less, because higher energy photons are less. And then you see the kind of, the hard spectrum. Okay? Then one problem which starts to be important in the case of gamma ray bursts, actually gamma ray bursts may have a strong magnetic fields. And then actually what I initially said that the neutrino energy carries 1/20 or 5% of the proton energy. This is not true at high energies. The reason why, because the pion already cooled. Because the pions, very, very high energy pions, you have a relativistic effect, right? So the pion lifetime is actually the order of the 2.6 times 10 to the minus 8 seconds, but you have a Lorentz boost, right? So if you high energy pion, you have a higher Lorentz factor, lifetime is longer, even in the comoving frame, and eventually the lifetime of the pions in the comoving frame becomes longer than the cooling time of the pions. The pions, because the charged pions, right? Neutrinos come from charged pions. And then because they have charge, the pions cool to synchrotron emissions. And basically, because of the cooling in the synchrotron emissions, the pion spectrum is actually suppressed in the cooling. Then basically, this energy is actually emitted as a synchrotron emissions. Then, as a result, the spectrum of neutrinos is something like this. So basically, low energy pions just decays. Basically, again, the same game. So the the quota of the pion energy goes to neutrinos. So I already said that the proton energy is here. Typical proton energy is 20 PeV. Then if you multiply the 0.05, you get 1 PeV. Okay. Then I don't estimate where this happens. Basically, this can be determined by the comparison between the cooling time and lifetime. But this is typically in the case of the GRBs as 30 PeV, but this depends on the details of magnetic fields. And then injected gamma ray spectrum, neutral pions, in this case is easy because gamma ray neutral pions lifetime very, very short. And it quickly decays. And basically, in this case, you can essentially ignore the cooling. And just you can say that the injected gamma rays are something like that. However, as I said probably before, in the case of gamma ray bursts, okay, PB gamma rays, huge, very high energy, right? These gamma rays cannot get out, usually. Then because the interaction with the gamma. Then basically, in order to calculate what happens, you need to do more sophisticated calculation. I will not discuss. Okay, so I think I have one more slide, probably, and then we'll finish. And then just for completeness, and I make a comparison between the detailed calculations and the analytical estimate. So if you do this kind of analytical estimate, basically you can estimate the neutrino flux within the factor of Hue. So basically this purple line is actually the if you follow this kind of calculation in a bit more sophisticated, but still similar. If you do the calculations in analytical ways, this is the purple line that you will get. And the realistic calculations by taking into account numerical effects is actually these red lines. There are basically the reason why you see the difference by a factor of 3 or 2.5, simply because that you just take the resonance effect. And actually, there's also that you have a non-resonant contributions, right? Then you need to take into account the other contributions. Once you take into account these, actually, you have more, basically this difference comes from this effect. Okay, so that's it. So basically, yes. Okay, so basically, what I did is that I discuss the source physics. Today, they're just using the 1 hour. So basically, I try to I discuss an example of the gamma reverse, in principle that you can for the exercise you can kind of apply this kind of the exercise to the different sources. Then you can estimate what is the expected neutrino flux. And but as I said, that for the inputs, it's very important to figure out the kind of important to include the information on the photon fields, and even in the one-zone model. And in reality, if you want to make a quantitative predictions, actually you need to take into account information from dynamics and so on. In this sense, actually, what you should keep in mind that there's there are many ingredients, even if you understand the particle physics part, and then you need to know which quantity, which kind of source physics you want to constrain. You want to know. I think this is important when you make a comparison between your theoretical outputs and the experimental data, and including the mass messenger and multiple length data. Okay, thank you very much. That's all.
So I'm sure there's plenty of questions for Kohta. Go ahead. Also because this is the last chance to ask him questions.
Hi. The relation between the pion energy and the proton energy? Relation?
This one.
Yes. Consider the multiplicity of pion or for only one pion?
This is no. This in reality is I just take the one pion, the characteristic pion. But in reality, it's not true at all, because the reality is basically something like this. Realistic situation. Yeah, I think so. Yes, this one. Basically, what I did is a very crude approximation. So that this is the x, and then x is the e pi, EP, okay? And then this is the energy distribution, okay? And then kind of this is the peak. And then of course, in reality, there's many low energy pions exist in real numbers, and very few high energy pions exist. But in this kind of treatment, basically, essentially, this implies that I did this kind of delta approximation. Now, all the energies, basically, if you integrate the distributions, they try to basically if you integrate this, and this is just gives kind of the inelasticity, basically energy fractions carried by pions.
I'm just struggling to understand about the photopion production efficiency. What exactly it is? What does it mean in terms of?
Okay. So it's better to go back to the. okay, it's better to explain this time, question. Okay, so basically, if you calculate the energy loss rate, right? This is basically for a given photon field, you estimate, how much energy is lost by the P gamma interactions per time, right? For the how much energy lost due to the pion production per time, okay? And then the question is that how much energy is lost, right? So the kind of energy transfer fraction within a given time in that can be estimated by multiplying the T dynamical time, because dynamical time is actually correspond to the duration of the photon emissions in one zone. Basically, if you consider internal shock, basically when shock is cried, when two shells collide, basically the shell is actually sweeps the material. Then basically crossing time is this. This is just say the dynamical time. Then basically photons keep generating, and then basically the protons can interact with during this time.
And we consider it also synchrotron loss in this?
Well, okay, so yes, for this kind of the realistic calculation, actually you have to technically everything. Basically, you are right, and then because for example, realistically, for example, when the protons actually protons may be cooled before if the cooling loss rate, the synchrotron loss rate is much larger than the P gamma loss rate. Basically, you cannot use a dynamical time scale, right? For the calculation, basically the available time is actually limited by this cooling time. So that you need to put the cooling time here to estimate the total flux of neutrinos.
Thanks. My question is about that type of GRBs, the low luminosity GRBs, because I don't know if I didn't understand, but you said that they have a very low luminosity, but I don't know, there was a graph?
Oh yeah, sure, I can show.
Thank you.
This one?
In the first slide, when you introduced that kind of GRBs, and no. The title.
This one?
Yes. That.
Okay.
But. Yes, because I had a question about the scale, but I see that. No, yes. Bueno, como escalado a 10 a la 50 hercios. Pero es que pensé que estaba, que eran luminosidades muy bajas, pero no me había dado cuenta que estaba escalado. Translate this part.
So should I explain this plot carefully to me?
No, solo que no me había dado cuenta que la luminosidad estaba escalada a 10 a la 50 hercios.
She didn't realize that the luminosity was rescaled. Yes.
10 to 50. Oh, right. Yeah. Okay. Luminosity. Yes. Oh, yeah.
Yes. Sorry, because
and this
that was a very low luminosity. And
yeah.
Sorry.
Yes, you're right. 10 to minus 3 is the luminosity. Yeah, this is 10 to 47 erg per second. So the luminosity is very low. Yes.
Okay. One more question. Oh, good. More questions.
Do you think that ultraluminous X-ray source might be relevant neutrino source without gamma rays counterpart, similar to shock jets in gamma ray bursts?
Yeah, I think it's possible. I think that there's a paper by Yoshinoue, I think, for the neutrino production in the ultraluminous source. But especially which kind of again, you need to specify where the particles accelerated, which which place are you thinking of? Which part? You are thinking of the jet or outflows?
I think that, for example, a shock jet in ultraluminous X-ray source is not possible.
Yeah, it's possible, but I think probably it probably depends on where the particles are accelerated. It's possible. So if you think that, for example, some people think that this kind of source has a wind, and then when winds, of course, when winds sweeps after material, and you have shock. And then in this case, in principle, the particles can get accelerated. And from the engine, there are a lot of X-rays supplied. And then it's possible to have some interactions between the high energy protons and the photons, the X-rays. But the problem that you need to specify you need to describe how the wind evolves. And if the density is too high, it's a problem again, because the shock may not be collisionless. And especially in the vicinity of the disk, and in the case of URX, the density is so high, and it's a very radiation-rich environment, which is, in this case, it is not so clear how the particles accelerated. At least for the Fermi, shock acceleration case. The connection is actually a different problem.
Anybody?
He has.
Good. 2 on the same side.
So these neutrinos, I understood that they are produced on the internal shock of the jet, right?
Yes.
But there is also neutrino production in the core of the supernova.
Yeah.
And these neutrinos.
Core or choked jet? What do you think about? Really core or just
the
supernova?
Core.
Just supernova.
Yes.
Or jet or supernova?
I'm sorry?
So which part that you are talking about the neutrino production in the usual supernova or jet embedded in the supernova?
On the usual supernova.
Okay, usual supernova. Well, again, the problem is that we don't think that neutrinos are produced. Okay, some are neutrinos, of course, produce. Mm-hmm. This is what we saw, right?
Yeah, but they observable.
High energy neutrinos are not produced. High energy neutrinos are produced related to the cosmic rays are no. At least when the shock is propagating inside the star. Because when the shock is propagating inside the star, the stellar density is so big. Initially, the shock is collisional. And plus, once the shock is actually mediated by radiations, and then we start to have a radiation-mediated shock. In this case, apparent any shock jump in the is very kind of smeared out by the radiation. In this case, you cannot accelerate the cosmic rays from the very low energies around close to the summer energy. And this is actually consistent, right? Because if particles are accelerated in such a dense environment, basically once the cosmic ray accelerated, they quickly lose the energy as a neutrino production, and basically shock is gone. Shock is dissipated. That is problematic. That you have a problem. But it's actually consistent. Usually people expect that the particle acceleration starts after the shock breakout. Once the shock breakout happens, then basically density is lower and lower. And actually, this probably depends on the shock profile, because if the envelope profile is too steep, basically when the shock breakout happens, radiation pushes the ambient material, and the material is accelerated. And again, you don't have a clear collisional shock. But when the density is actually, density profile is actually relatively shallow, like a wind profile, in this case, once the shock breaks out from the star, and in this case, if you check the conditions, the shock becomes not radiation mediated. And it's kind of natural to expect that the collision-less shock is formed and in this kind of situation. And still, you need to check that the Coulomb loss time scale. But this is actually one of the interesting topics, because now the many observations show that mass loss is very common, and even for the type 2p supernova, a lot of mass is there. And if you ask that, if you believe this number, for example, you can ask that how many neutrinos are expected in the high energy neutrinos can be expected for galactic supernova. But if you believe the recent observations of the optical observations, apparently the mass loss is very common. And then 10 to the minus 3 or 10 to the minus 1 solar mass exists just in the vicinity of the progenitor star. And then dispersion is small, right? Because still the 10 to the minus 3 solar mass, 10 to the minus 1 solar mass is small compared to the ejector mass, which is 10 solar mass. But tiny fraction can be accelerated, and then this is enough to detect the high neutrinos. And then if you pick this number, basically the IceCube can detect 100 to 1,000 neutrinos in TeV energies. If you assume that 10% of the kinetic energies go to 10% of the kinetic energies go to the cosmic rays.
If I can quickly add one thing, this is exactly what the neutrinos produced in the supernova are the ones that we were talking about in the first discussion session that the Pasquales were mentioning, that they would push the star. Completely different energy. And in fact, if you had done the exercise that I was giving you, you would have found that the mean free path is much smaller. So it doesn't matter what energy you produce them. Well, you produce them at low energy, but even if you were producing them at high energy, since the mean free path is so small, they would thermalize. And therefore, they will get the thermal energy of that ejecta, which is 10 to 7 or 10 to 10K, which is 10 MeV, okay? So these are two things that you're talking about in this moment.
Kohta-san, can we see the plot on just before your summary, which shows the neutrino mixing profile?
Which part? The neutrino part?
I think it was the second to last slide. Or yeah, just before. Before this. It had before neutrino mixing and after neutrino mixing.
Oh, this one?
Yeah, this one. I'm just trying to understand this feature that is happening around PeV. We haven't really discussed neutrino versus anti-neutrino and flavor information here.
Yeah, I didn't discuss neutrino, anti-neutrino flavor here.
But it seems like this is happening around the resonant cross-section.
Here?
Yeah, for nu-E bar.
This is actually not neutrino, anti-neutrino. This is actually come from the difference between the neutrinos, muons, and pions.
Is it muon and pion only?
Yeah, because I think that you imagine that what muon lifetime is actually the 2 times 10 to the 10 to the minus 6 seconds, right? And which is longer than the pion lifetime.
Yeah.
And basically this means that for given, the mass is comparable, and then for the given time, basically the muons can cool more, right? And then typically, then basically you have a neutrinos coming from the pion decay, then basically you should have neutrinos coming from the muon decay, but in this part basically you only have neutrinos from pion decay, and the low energy you also have neutrinos from muon decay. And then this actually has a kind of dip. But in reality, it's actually because if you go to high energies, and then multi-pion production happens, as I said, and then this actually tries to fill the dip.
Any last question for Kohta? Well, then I guess it's a good moment to thank him again for the classes and the colloquium. That's his last class. And just to show him like a very small token of our big gratitude.
Okay.
Thank you very much.
Thank you very much. Thank you very much. Thank you very much. And I enjoyed this lecture, and I got a lot of questions. So please let me know if you have more questions freely. So just send me an email, and then I will put the slides.
The videos are already online. Probably they have like a 24 hours delay, but they should all be online. And if you send me also the slides, I will actually, they will all be online.
I had to skip some slides for some short neutron star merger stuff, and then maybe you can check this kind of slides.
So thank you, Kohta, very much again. Okay, so let's take a break, undefined 10-15 minutes, and then I will call you back for the poster session. Okay, I set up the whole thing, go free, and I will ring the bell.